Welcome back to ECE 442-542. Homework number 1 solutions are posted on D2L. I don't know how many of you had to go look at those or find those, but hopefully you found them if you were looking for those. They are in Unit 1 underneath the homework assignment itself is where I've tried to locate solutions to homework number 1, and that's the strategy. And obviously next week, when homework number 2 is due, I'll try to get the solutions up fairly fast because our exam number 1 is a week from today. So a week from today, you'll be coming in getting ready to attack the exam that will be given at this time. I'm also going to try to offline some material, and that material is the z-transform of an exponentially damped cosine. I'll derive that. I thought I'd gone through enough derivations last time with the common waveforms, but the exponentially damped cosine waveform is something that damps exponentially, and it has some oscillation based on this damped frequency of oscillation omega sub d. And I'll try to make that available or post that somewhere in line with tonight's lecture, maybe in between last lecture and this lecture, because that's sort of where it fits. But it's yet to be recorded. Hopefully I can get some time. I can step out of my other roles and do some recording. We will have a review session for exam number 1, and tentatively I'm just assuming we have this room. I haven't seen anyone else coming in after us in the last couple of weeks, so I'll try to put in that request. But if you have topics or questions that you would like to see addressed during the review session on Monday night, make sure and submit those before Sunday night of, well, after the Super Bowl, I guess. Isn't that Sunday? So maybe while you're watching the commercials, you can think up of a question or a topic that you would like covered on exam number 1. And there's a quiz section in D2L, and I've made it as a quiz so that you can type in your question as a free response in that area on D2L. There is also review material for exam number 1, and that's in its own unit on D2L, and I think that's directly below the unit for unit number 2, which is the z-transform unit. And what we want to do today is basically walk through some properties of the z-transform, and that's to help you put together a z-transform expression that you may not find directly in a table. You should become very comfortable matching up a time domain waveform with a row entry in a table, and I'm saying in a table, you find the one that makes you feel the most comfortable, and then determining what its z-transform is from the table, but there may not be a direct match. And these properties are designed to help you figure out, how do I generate a z-transform that's not quite like it is in the table. And then we will get into a topic that I'm calling frequency response for discrete time systems, and we'll do that via a low-pass filter. And we'll then design a low-pass filter in the continuous time setting. And if you've read chapter 1 of that one chapter that I put in unit 1, you should feel comfortable with designing a low-pass filter. We'll change our bandwidth. By the end of the class, hopefully we will have a linear difference equation that will implement a low-pass filter, which means that now you could simply code in that difference equation, put in a string of numbers. Obviously that string would have had, or that waveform representing a sequence of numbers would have to be sampled consistent with our sample period, but then out of that difference equation you would be getting this filtered signal response, and that's what we hope to finish with today. But as I said, before we do that, let's go through some properties associated with the Z transform. And I'm really just trying to establish notation here. Capital X of Z is this summation from minus infinity to infinity in general of this sequence of numbers, little x of n. That's some time domain sequence scaled or weighted by this complex number Z raised to the minus n. And I may get lazy, or I'm not sure it's called lazy, but more efficient, and simply say capital X of Z is defined to be this script Z of a time domain waveform, and those are equivalent relationships. I could say the script Z, and you can now, in its place, put this infinite sum. That's what I'm trying to mean by this notation. Let's look at a property I'm labeling as the first property, linearity, and that's if you question? So now the question was, a lot of times when you're doing the Laplace, we're integrating from t equals 0 to infinity. Here I'm saying let's just define this Z transform more generally and go from minus infinity. So it would be like taking the Laplace transform from t equal minus infinity to infinity. You're most familiar with the one-sided Laplace. We will do a lot of one-sided Z transform where the lower limit will actually be 0. But if somebody starts asking you questions and you look at them like, I've never seen a two-sided Z transform, they might wonder where you learned your Z transform. So let's go ahead and make it as general initially as possible, but like I said before, this is a controls class, and a lot of times we do define some location in time as our 0 time, and we move on from there. And in that case, the lower index on the summation will be starting at time 0. And you'll see that play out as we go through some of these properties, actually. But for now, let's just assume, unless otherwise stated, that your Z transform can be associated with a waveform that starts at minus infinity. I never know which side you're going from minus infinity to plus infinity. But if minus infinity is on your left, then plus infinity is on your right. And we'll maybe see some of that as we go through now. But here, let's say that we had two sequences, an f sub 1 and an f sub 2. These are two waveforms that are discrete. That's the little nt, and sometimes I might implicit or just not include the capital T. Sometimes I may just say f sub 1 of n. Then you will have to have that t on the side if it's important to know what the sample period is. And then I'm weighting those two sequences with two different scalars, an alpha 1 and an alpha sub 2. And I'm trying to find the Z transform of that linear combination. And I think you can anticipate, based on this definition for the Z transform, what's going to happen. That summation is a linear operation, just like the integral is a linear operation. And now this Z transform can be pushed through and looked or applied to this summation individually. So that you can now say that here, the Z transform of this linear combination is equal to alpha 1 times the Z transform of the sequence f sub 1, little f sub 1, plus alpha sub 2 Z transform of f sub 2. And now by definition of that script Z, we can see then that this is just alpha 1 f sub 1 capital F sub 1 of z, which is the z transform of the sequence little f sub 1, plus alpha sub 2 f sub 2 of z, which really says that if you know the z transform of little f sub 1 and you know the z transform of little f sub 2, you now can linearly combine those and find the z transform of their linear combination by using this property. What you will want to just be aware of, and I will just say watch, the region of convergence when you combine these. It may change. It's not going to be the same because the region of convergence for capital F sub 1 of z and the region of convergence for f sub 2 of z may not be the same. And when you put them together, it could be, well, the region of convergence will be at least as big as their overlap or their intersection. But watch the region of convergence. It could change. And we won't spend time on that right now, but I think as we do work through more of these, it'll become a little bit more clear what we mean by these regions of convergence overlapping or their intersection. The second property is everyone's favorite, convolution. I think everyone likes to do time domain convolution. Not. That's probably why you like this property, because now what are we doing? We're actually converting this time domain operation into something in the frequency domain, and the reason we're doing it is because it's probably easier to perform the analysis in the frequency domain. In the time domain, the convolution is this summation. Let's say it's from L equals 0 to n, f sub 1 of L, f sub 2 of n minus L. We want to actually find the z transform of that, and we can do it if we have the z transform of those individual sequences. And it will be consistent with what you've done in the S domain or with Laplace. This will be the product of the z transform of little f sub 1 with the z transform of little f sub 2. And this allows us now, if f sub 2 represented a system, f sub 2 of z was the transfer function of a system, and f sub 1 of z was maybe this waveform that we wanted to excite, or it's the z transform of the waveform that we're exciting the system with, then we can find the z transform of the output by multiplying those transforms together, consistent with what you've done for the analog case. A time shift property. And we actually used this last lecture. Here, let's look at the z transform of f, and instead of n, let's shift that, either advance or delay that in time by some fixed integer amount of time periods. So I'm going to do that together, meaning an advance would be a plus and a minus would be a delay. And that way I can put all of these into one equation instead of two separate equations. Now, what I should do probably to make this more explicit is actually include in here a window that turns this off or on at a particular point in time. This U is a window, and I'm using this as the unit step. And I'm actually going to be referring to this as the waveform itself is aligned with the window. meaning if the waveform is delayed, let's say by 2 units of time, so n minus 2, then we're actually going to go ahead and say, let's look at that, or turn that on with this switch, this unit step, that's also u of n minus 2. And so the window is aligned with the waveform in this particular time shift Z transform. If this is the case, then we won't have to worry about adding in additional terms. The initial conditions will be gone, and this will simply correspond to Z, where Z is an operator that either looks like an advance or a delay, depending on the sign of the power, and how much advance or delay depends on the integer L, times the Z transform of the original waveform, little f of n. In this is the time index, and this is a fixed integer. In the last lecture, we had y, or little y of n minus 1, little y of n minus 2, which meant we were delaying y by 1 sample period or 2 sample periods. Question? So the question was, I'm paraphrasing or rewording this, but you can sort of, going back to an earlier question, view that unit step like you're cutting off half of your time waveform, or your waveform f of n, and the next one will look even more. But what's really happening, or I don't know if I can do this very quickly, but let's say this is now our f of n, which is doing this. And this unit step, let's say that L was equal to 2, then we would go over here and, well, this should be aligned, but I'm making it offset so that you can see the difference. Let's say this is minus 2. This thing is on now, and it's throwing away everything that was to the left of where that unit step kicked on. Here is now u of n minus 2. I don't know if that helps or not, but that's, now it's saying, forget about what's to the left. We just want to Z transform everything that's on or underneath or windowed by this unit step that's delayed by the same amount. And in fact, maybe what I should have done, well, I won't. I'll just say there's f of n. And we'll figure out how much you needed to delay it depending on your particular problem. That's the easy one, and this is the time shift property you would use if you were trying to find a transfer function, because we don't worry about initial conditions when we're trying to find a transfer function. We just worry about the amount of advance or delay, and we scale that transform by the appropriate advance or delay. Yes? So let me see, the Heaviside function, what are you wanting to say about it? So this is like the Heaviside function. This is a unit step, and that's what I'm calling it instead of calling it something else. I'm just calling it a unit step function, which I can now advance or delay depending on what my argument looks like, or what's in my argument. Now, if that one should have been fairly clean, but let's suppose that I do the following. Suppose that I now do f, and I will just do this for the delay, but you can do something similar for an advance. But now let me say that I want to start this at the origin with my window. Irregardless of how much I delay that, I'm going to start it at the origin. This now has a little bit more involved expression. It does have a z to the minus L f of z, but now we need to include these initial condition terms, and I will put all of those together in a summation. And this is the lowercase, whoops, using f, so here is f of minus m equal 1 up to L, and that's weighted by z to the m minus L. But this is similar to how you had to keep track of the initial conditions when you were looking at the Laplace transform of a derivative. Let's look at an example and see if that might help. Hopefully it will help. But this particular case, I'm going to say the window, how do I want to say this? Let's say this is the window at time 0. Where I'm turning this on is at time 0. Suppose somebody wanted to find the z transform of y of n minus 1 u of n. Then if you simply apply this property, that says that you would have z to the minus 1, little l is 1 in this case, times the z transform of little y of n, which is capital Y of z. And let me just go ahead and do this in all of its glory. From m equal 1 to L, which is 1. So I'm really overplaying what's really happening, but I'm summing from 1 to 1, so I really should just have one term in that summation, but you can hopefully see where the L is being positioned. Y of minus m, z to the m minus 1, where L again is right here, and that's going in there, and it's also going in there. That says then that you have z to the minus 1, capital Y of z, plus, we evaluate this with little m equal to 1. Now we have to include y one time step before the origin, which is y of minus 1. And what do we scale it by in terms of the complex z? What is m? 1. So we have z to the 1 minus 1, z to the 0, so we don't even have a scaling of z. We just have that initial condition term out hanging on by itself. And that should look similar to what you would do when you would Laplace transform a derivative, except here we have a plus sign, and in the other one we might have subtracted y of 0. But that's the idea behind this property, is you need to worry about whether your window is aligned with the advance or delay of your function, and if it is, it's a very straightforward property. That's this one. And if the window starts at the origin, then you have to pay attention to the initial conditions. And we'll look at how we can solve difference equations using this second property. We've already used the first half of this property to find a transfer function, where we could neglect initial conditions. Another property, property 4. This I'm calling scaling. In the z-plane. You might see this written several different ways, and that's why I'm going to go ahead and include many different ways of writing this, you might see the scaling in the time, or the weighting in the time domain written as r to the minus n. So for each time index, you have some scaling going on. Or if that negative exponent looks weird, what you can do is you can say, well, that's just 1 over r to the n, f of n. Or that's the equivalent to taking f of n r to the n. And that, if you could identify an r factor raised to the n scaling your time domain waveform f of n, you could immediately write down its z transform. You would just, everywhere you had a z in your original capital F of z, you would replace that z with r times z. Suppose you have this sequence. Little f of n is equal to a of n, and here I'm going to hit, and assuming this is one-sided, what's the z transform based on last lecture? What's capital F of z? Maybe we didn't use A, maybe we used R, but now just replace the A with the R, or vice versa. Replace the R with the A. Now you have 1 plus A squared plus A cubed, except those are all weighted by z to the minus 1. So you have 1 plus A z to the minus 1 plus A z to the minus 2. What did that end up being? That or that. Does that look sort of familiar from last time? That's now little f of n. What if somebody now said, oh, I want you to find the z transform of g of n, where g of n is now f of n weighted by, or dividing by, r raised to the n. Plug in an r value, let's say of 2, and what's this doing? Now you're dividing by 2 to the 0, which is 1, 2 to the 1, which is 2, 4, 8, 16. You're chopping this f of n down more rapidly. It's decaying more quickly if little r was something like 2. So you're just exponentially weighting this original f of n by something a little bit more powerful. So this, depending on how you want to write it, this is now r to the minus n f of n, so that this fits exactly with the first z transform, and that says that we should be able to find g of n z transform by doing what? That's kind of confusing, isn't it? So, but that's really sort of what we're doing. We now need to replace our f of z that we had with that. And does that seem to make sense? This, you could factor out an r from the numerator and the denominator and cancel it, and you have z over z minus a over r. And that's really what you have with g of n. It's now a over r, both raised to the nth power. And if you wanted to make it even more concrete, maybe you could let a be 1/2 and r equal 4. If numbers make you feel a little bit better. And then you could see the relationship between, or the application of this property. One more property. The final value theorem. If capital F of z converges for the magnitude of z being bigger than 1, and all poles of z minus 1 times f of z, which really means that if you had a pole factor in capital F of z at z minus 1, it's going to get canceled by that factor that you're scaling it by, which is z minus 1. If all of the poles of this new expression, z minus 1 capital F of z, are inside the unit circle. So these are the assumptions, or these are the conditions that have to hold before you can apply the final value theorem. Then you can find your limiting value of little f of n as n approaches infinity by evaluating the limit as z goes to 1 of this factor little z minus 1 times the z transform capital F of z. Why do you want to have a final value theorem? What good is it? Is there anything good about it? Just looks confusing, huh? Why would we want to have a final value theorem? What's the advantage of this, or what could be an advantage of this? It's going to tell you where you're eventually going to go to, right? If it goes to something constant. If it violates these assumptions, then you can't apply the final value theorem. But if it satisfies these assumptions, then you can find where you would eventually end up without having to inverse Z transform and do all of that algebra or that computation on capital F of Z. You could avoid that by just evaluating this in the limit as Z goes to 1. And that's easier or quicker or cleaner. Let's say that this capital F of Z was fourth order. You could have to do a partial fraction expansion on 4 terms, find their residuals, and then do the inverse Z transform. Well, here you just look to see where are my poles. Are they well behaved in Z minus 1 times F of Z? And if they are, boom. Let Z go to 1 in this expression, and that's where my time sequence is going to eventually end up. That's the advantage of the final value theorem, or one of the advantages. It can save you some work. Now, transitioning, that's sort of assuming that you're going to some constant location. Let's say you're going to 2. What happens when you hit a system with a sinusoid that doesn't decay. Let's say it's a stable system and you excite it with a sinusoid. What's going to happen at the output of that system? Actually, this is all electrical. There's nothing. So if I shake this, so you're not going to get dizzy by me shaking the table, even though it's shaking my tablet. But if that was a consistent sinusoid, so now if you're playing at home, you might go over to your kitchen table and start shaking it. And what's going to happen? A leg will fall off. So now a leg has fallen off. But what happens as you're shaking that? The table will, if it's a linear system, what frequency will it shake at eventually? When you start shaking that table, it naturally has modes that it wants to shake at, doesn't it? It has natural modes. Those are the poles of your transfer function. But those, if it's stable, those will decay to zero, and what's going to happen? You'll finally hit a sinusoidal steady state, and that system will just shake at the frequency that you're exciting it at. And what you want to know is, how does that system behave? Does it attenuate or does it amplify that particular frequency when that system is shaken at that particular frequency? And how does it shift in time? Do you remember doing this in the continuous time setting? Finding the sinusoidal steady state response? I wanted to see a lot of heads going up and down, but if you haven't, that's okay. We'll learn it here, okay? So let's now look at, or what happens if you do this for a lot of different frequencies? Suppose you did this for a speaker at your home. You put in a sinusoid and you look to see how that speaker behaved, and what do you really want? You would like that speaker to be fairly accurate in its representation of the signal that you put in, depending on the frequency that you put in. If you do that for many different frequencies, you're finding its frequency response, the Bode plot associated with your system. That's what we want to sort of be thinking about. We want to look at the discrete time frequency response. And before we jump into the discrete time case, let's go back and remind ourselves where we've been, hopefully, or I'll connect you with something that maybe you're a little bit more comfortable with. Let's now say, here's the connection. With your previous knowledge. Or here's a question. How will a sinusoid be filtered by a low-pass filter? And what's your default answer? What is the frequency of the sinusoid? That's not what I was getting at, but that's the correct, one of the correct responses. You need to know the frequency of the sinusoid, and what do you need to know relative to that frequency? The frequency of your cutoff on your low-pass filter, right? So I was thinking a default answer, how will a sinusoid be filtered by a low-pass filter? I would say it depends, right? It depends on the frequency that you're exciting it with, and it depends on the cutoff frequency of your low-pass filter. those two depend on each other, and how it responds depends on those two quantities. So you could give the default of it depends, but let's work through this and see how it actually does depend. First, let's go ahead and design a first-order low-pass filter. And again, we're doing this in the analog setting. And I could have said a passive low-pass filter, and I hope, since you are all well, no, I guess you're not all electrical engineers, but you're taking an electrical and computer engineering class. So after this class, maybe somebody would expect you to know something like this. What do you see, what comes to mind passive circuit-wise when you think of a low-pass filter? Pardon? An RC, a resistor-capacitor combination. There's a low-pass filter. Here's the input, and there's the output. And maybe you don't like that in the time domain, you don't like those T's, but you can put this into the frequency domain. You can do the S domain equivalent circuit, which looks like what? It looks a lot different, doesn't it? No, but the impedances do maybe look a little different, especially with the energy storage device. It now has an impedance of 1 over SC, and we can now change those T's to capital letters. And what do we want? Now what we want to do is find the transfer function between the input and the output, and that transfer function will be the transfer function of our low-pass filter. And it has one energy storage device, it's first order. Apply your favorite circuit analysis tool. And don't tell me you don't have a favorite. You like them all. All right. So do however you want to analyze this, but you could use a voltage divider or KVL. And what would you do? Let's say voltage divider, V sub 0 of S. That's going to be the impedance of the capacitor divided by the sum of those two series impedances. And maybe you don't like to have ratios of ratios, so you want to clear the fraction in the numerator and the denominator, put everything over a consistent denominator, which in this case is SC, and cancel the SC in the denominator of the numerator and the denominator. Can I say those anymore? But multiply by 1 SC over SC and you get the same thing. Our transfer function, capital H of S, is now 1 over SRC plus 1. That's our low-pass filter. And if you wanted to, you could bury those two parameters into one variable called the time constant, and we'll call that tau. So you might see this as 1 over S tau plus 1, or 1 over tau S plus 1. That's a continuous time transfer function in the S domain, and it's parameterized by one pole. Let's now change that just a little bit. Let's create a low-pass filter with a bandwidth of, and here I'm going to put in a sort of, I don't know, a fudge factor. I'm going to say of about 100 hertz. The about is going to arise because I'm going to get tired of using pi. I'll just replace it with 3. So that's where the about comes from. I'm going to, when I see a pi, I'm just going to replace it with 3. So I want a bandwidth of 100 hertz. That says then that the cutoff frequency of my filter is 100 hertz. But when I'm playing with S, I'm in radians per second, not in cycles per second. So I need to convert this into omegas, and that's just 2 pi f sub c. 2 pi over 100, so this is now 200 pi. And here is where I'm going to do my about. I don't want to worry about 628. I don't want to keep track of that many digits. So I'm just going to throw away the 3.1, the 1.4 and the 3.14. Or I'm going to say this is now 600 radians per second. And that's going to be good enough for me. That's going to be my bandwidth of my low-pass filter. It won't be exactly 100 hertz. Are we okay with that? Now, how do we put this information into our transfer function? We had an H of S that had an RC or a tau. How do we plug or change this? Or how would we eventually find the R and the C to make this actually have a bandwidth of 100 hertz, or about 100 hertz? We need to somehow specify tau, right? The time constant. And we have enough information since somebody's told us the bandwidth that they want. Or we can now look at the denominator of H of S, which is this SRC plus 1, or that's this tau S plus 1. We want to know where's the pole. That's what we're trying to fix by setting a bandwidth of 100. And the pole we can find by evaluating this expression or setting that denominator equal to 0. And it now has a pole in terms of tau of minus 1 over tau. What do we want that? Where do we want that pole if we want a bandwidth of about 100 hertz? We want this to be at minus 600. That was our cutoff. That was our omega c value. Now, from that, we can solve for the time constant tau. Tau is just 1 over 600. Or 1/6 times 10 to the minus 2. Maybe I don't remember what that is, but I can sort of back it out. Now I have 1/3, that's 0.333, and divide that in half. So now I'm at 0.16. Is that okay? So this is now 0.1667 times 10 to the minus 2. That's a time constant. That's seconds. So our tau is now this let me put my decimal place in the right location. So I squeezed another 0 in there. I needed to shift over 2 with the 10 to the minus 2. Now I have my transfer function specified to give me a bandwidth of about 100 hertz. H of S is 1 over 0.00167 S plus 1. What's the DC gain of that transfer function or that filter? What frequency are we at DC? S is going to 0, isn't it? So if we evaluate this transfer function at S equal to 0, we will get our DC gain. So this is now a DC gain of 1. Well, because we're going to do something similar when we find the discrete time transfer function. Let's look at this in the frequency domain. Verification of the the low-pass filter in the S domain. Instead of writing 0.00167 times S, I'll just say S over 600. And that's now in time constant form. My tau is 1 over 600. Or, so this is the transfer function in time constant form. When's that useful? Or when might you like to have a transfer function in time constant form? Bode plots. So now if you wanted to draw a Bode plot, this might be a nice form to be in. If you're trying to find the pole zero diagram, then you actually might want this in a pole zero form, which we can find by simply refactoring or scaling it by 1. And this now becomes 600 over S plus 600. Where this is now in the pole zero form. We have pole factors and zero factors. We can immediately evaluate the denominator and figure out where our pole is located. We just find the values of S that cause the denominator to vanish. How many finite zeros do we have? Do we have any finite values of S that cause the numerator to vanish? No. Pardon? No. So we have no finite zeros. Some people might talk about infinite zeros. You do have a zero at infinity. As S goes off to infinity, H of S vanishes. And you want H of S to vanish at 0. That's what the definition of a zero is. But there's no finite value of S that causes that to vanish. There is a finite value of S that causes the denominator to vanish or for the thing to blow up. h of s to go unbounded, and that's the value s equal minus 600. And this is useful if we're looking at a pole zero diagram. If we're sketching a Bode plot, bless you, sometimes it's helpful to know where are we starting our magnitude. And for low frequencies at DC, that's where we're starting with a low-pass filter. And we just found the DC gain of this, and that's 1. In terms of dB, what is 1 in dB? 20 log of 1, log base 10 of 1. What's the log of 1? 0. So now we're 0 dB on our Bode plot. This is now the magnitude of h of j omega in dB. And then what happens? Are we just flat at 0 dB all the way out to infinity? Now fall back on, oh, we're doing a low-pass filter. What would you know happens with a low-pass filter? The frequency has to start rolling off at high frequencies, right? But do we know where that is going to happen? Pardon? At omega. What omega? So now we have our omega is 600, isn't it? So now we know when we get out to 600, we will start to go down. And this is a real filter. It's not an ideal. In an ideal, you would just drop off to 0. But here we have a first order, and now that determines how quickly. So this is happening at 600 radians per second. Here is our, let's say, log of omega, or omega, depending on how you want to label it. But how fast are we rolling off? Minus 20 dB per decade, or minus 6 dB per octave, depending on if you're singing. So now we have what's an octave? It's 8 whole notes, right? But it's actually a factor of 2, where a decade is a factor of 10. So now if you needed to know where you were at, let's say at 1200 radians per second, you now know you would be 6 dB down, and you wouldn't have to always be working with decades of frequency. You know where you're at 6,000, right? You're 20 dB down from 0. You're minus 20 dB. You know where you're at 60,000. Well, now knowing that it's the same as 6 dB per octave, you can chunk that up in finer degradations. And now instead of at 600, you could say, oh, at 1200, a factor of 2, I'm going to be down at minus 6 in dB. That's why you might like to know 6 dB per octave or 20 dB per decade. Now, what's the phase look like? At low frequencies, go back here and say, okay, at low frequencies, what's the phase of h of j omega when omega is small? And small could be an extreme. We could say it's 0. 1 over 0 plus 1. What's the angle? What's the phase of 1 over 1? What's the phase of 1? 0. What's the phase of 1 in the denominator? 0. We have 0 minus 0. We have 0 degrees. That's where we're starting. That means we are lined up at low frequencies. With the input and the output, they're lined up. There's no time shift. There's no phase shift. So we're starting our phase at 0 degrees, and at high frequencies, where is our phase going to end up? Minus infinity, like the magnitude. How much phase is contributed by one pole? 90 degrees. So we're going to eventually get to minus 90. And what's the sort of the rule of thumb? Well, we spread that 90 degrees over 2 decades, and that 2-decade interval is centered at the break frequency. So at the break frequency, we're actually at minus 45 degrees. A decade above that, we're just going to assume in our straight line approximation we're at minus 90, and a decade before that, we're going to assume we're at 0. We've drawn our phase curve. Now we have a phase. If I can get this back, and now you have to just sort of believe my, let's say that's 60, and this won't be necessarily, oh, that's supposed to be symmetric. I'm on a logarithmic scale. Okay, so it's not so, I told you, don't hold me too tight to getting this accurate. So now you're saying, okay, there's that. What's that? Oh boy, now I have to. This still probably looks terrible, but up close it looks really good. So this is 600. This is 6,000. This is minus 90 degrees, and this is 0 degrees. This is now at minus 45 degrees. Pardon? Okay, we're engineers, but we would get a straight edge out and get rid of that kink down there, but you can do a little bit better than I did. But now what do we do? Well, now we know how the system, this low-pass filter, this first-order low-pass filter, we know how it behaves approximately for every frequency, from DC up to as high as we want to go. And now we can talk about that in terms of this block diagram representation. Suppose now that the input in the time domain is 2 cosine 500t. We now apply this input to our low-pass filter that has a cutoff frequency of 100 hertz, about 100 hertz. What's the output going to look like? And I'm going to tell you that you have the answer staring you in the face with the Bode plot. Meaning you can go back here and you can say, oh, at 500, I know what the magnitude change is going to be, and I know what the phase or the angle change is going to be, so that I can immediately write down that V sub O in the sinusoidal steady state after the initial transient, it's going to be the magnitude that I injected, which was a magnitude of 2, times h of j 500. So I evaluate that transfer function at the frequency that I'm exciting it at, which is 500, cosine. What's the frequency of that cosine? In the sinusoidal steady state, all the transients have disappeared. How's that filter shaking? It's shaking just like you shake it, right? You're shaking it at 500. It's going to be outputting a cosine that's shaking at exactly the same frequency of excitation, which is 500. And then we have a possible offset due to the phase of that low-pass filter. And that offset is at h of j 500. This is now omega 1. Somebody, when I said, what's the low-pass filter, they said it depends on the input frequency. The input frequency in radians per second is 500. Omega 1 now we know, or we've been told, so this is omega 1, here's omega 1, and here is omega 1. We just need to know the magnitude at that frequency and the angle at that frequency, and that information is available to us from the Bode plot from the frequency response. Or, if you wanted to, we could find it in the pole zero diagram, in the S-plane. For the low-pass filter, where do we plot? Now we're doing X's and O's. Here's our pole zero diagram. Do we have any finite zeros? No. Do we have any finite poles? Yes. We had a pole at minus 600. Now what? Well, now, if you remember talking about the circus tent, we have an infinite pole sticking out at that pole location, and we have a rubber sheet on top of it, stretched on top of it. Now to find the frequency response, we start at DC, which is the origin, and we just walk up that imaginary axis. We're evaluating that system at j omega for each omega. So we just take little steps along this imaginary axis, and we can evaluate the system's frequency response at each frequency omega. And which frequency are we interested in? The input frequency, omega 1. So we now need to walk up here an amount consistent with J500. And then we can get down all of our drafting tools. We can get our protractor and find that angle, and we can get out our ruler and measure that length. Or we can use our calculator and find that hypotenuse, that's L sub p, and we can use our trigonometry to find that angle, theta sub p. So now we know, that's why we did all of that preliminary math, is so all of that's second nature, right? We know Pythagorean theorem, we know trigonometry. We can figure out L sub p and theta sub p. And knowing that allows us then to really calculate this complex number h of j 500. This is now 600 over j 500 plus 600. This is now in pole zero form. Or this is now 600, and now we can rewrite that complex number, change it from rectangular form, which is what that is, into polar form. We can find the magnitude of that, and the magnitude of that is really just L sub p, the length of that hypotenuse, and its angle is theta sub p. So that now we have 600 over this hypotenuse, and the angle is now how much we have to look up and how far we need to go horizontally. So it's up 500 over 600. Doing all of that, we end up with 781 at an angle of a little less than 45 degrees, since it's 500 over 600, 39.8 degrees. We can divide the denominator into the numerator, and now we see that at 500 radians per second, this low-pass filter will actually give us 77% of what we put in at 500 radians per second, and it will offset it consistent with an angle of minus 39.8 degrees, or V sub O of t is now 2 times, because we started with 2, we take 77% of 2, and that ends up being 1.536 cosine, we're still shaking at 500 radians per second, minus 39.8 degrees. Now that first term in the argument of the cosine is in radians, and the second term is in degrees. So you'd need to, if you were computing this, you would need to make sure whatever your calculator was in, the units of, you would make sure both of those were in the consistent units before you found the cosine. And that's for each time. Or you could factor out that 500 and you could find the actual time delay, the time shift between the input waveform and this output waveform. You put something in at 2, and now what happens? You get the same waveform, 500, in terms of sinusoid. It's just attenuated a little bit. Now it's at 1.5, and it's delayed in time a little bit by that angle of delay. That was all review. Yes? Now what? We want a low-pass filter in discrete time, don't we? We want a difference equation. We want a low-pass filter in discrete time. Deer in headlights. Now what do? Well, we have the transfer function. We have v sub 0 of s over v sub I of s. That's this 1 over tau s plus 1. I can cross multiply, and I can now have tau s plus 1 v sub naught of s is equal to v sub I of s. And I can now put that into the time domain. Yes, I can inverse Laplace transform. I now have tau weighting the derivative of the output voltage. I now have tau v sub 0 prime of t plus v sub 0 of t is equal to v sub I of t. And if we ended up with a third order differential equation, we might start scratching our head a little bit more. Because we had a first order low pass filter, we better just have a first order differential equation. And we do. What we now want to do is somehow convert this into a difference equation. And the way that we're going to do it is we're going to approximate that derivative. What's the derivative? dv naught dt, some differential change in the voltage over a differential change in time. Well, we can quantize that and come up with a difference equation. And we'll do it here very crudely, but we'll look in later parts of the semester, we'll look at all sorts of different ways to find what we call discrete equivalence. Here, I'm going to say a crude discrete equivalent is what we're going to do. We're going to actually let this derivative v sub 0 prime, which is dv naught of t dt, we're going to approximate that as v naught of n plus 1 capital T minus v naught of nt. There's a small change in our output voltage divided by a consistent small change in the time. And we can clean up that denominator. The denominator just becomes capital T. So I'll let you go home and come up with a first order difference equation that replaces this low pass filter, and now you can code that up and you have a low pass filter that you can play with all weekend. I'll see you on Monday.